Hello, this is DC here. Welcome to video number 3 on SRI512. In the last two videos, we saw the structure of SRI512 tag. We have also used the development board based on ACR122u, and we saw how to do the read and write. In this video, I'm going to show you how to use this tag and using the learning kit, and here I'm going to show you in detail the various sections of this memory. We have seen this diagram in the previous video. So any SRI512 tag has got 4 sections. The top 6 blocks have got a resettable OTP bits, followed by 2 counters, followed by the user memory, which are lockable, and eventually you got one more block which is called system area, which has got the locking bits and some reserved words, reserved bytes, and followed by the fixed chip ID. So I would not like to now make any changes to this bit because you might end up losing the flexibility of the tag. Now we are going to understand in detail and how to work with these areas. Most of the information I discuss here is same what I discussed in my SRIX4K video. So a couple of things we need to understand here. The first 4 blocks are OTP, and it is also called resettable OTP. It means when all these bits are used up, you can reset it back. So that's why it's called resettable OTP. You got 2 counters. The block 5 is a normal counter, and the block 6 it's a counter with some special features that controls the resetting of the OTP. And there's nothing special about user memory. Most of the time these are written with some encrypted data, and we have got the log bits, and we have seen this tag has got 16 log bits, and each bit controls the individual block. Now once the block is locked, we cannot unlock it. So with this background, so I would like to take you to this the software. We have seen this software in so many videos, and this is the older software we have written, and I'm going to use this first, and later on I'm going to show you with how to use this with the other reader writers. Now I've got a brand new, you can see I've got a ACR122. Sorry, I'm using ACR122 device in this video and in software. So I've got a brand new, probably now I've used this tag in my previous videos. Now this time I've got this stuck to a plastic PVC card. Now because of the way this software is written, so before you select the SRI tag, you have to place any ultralight in any MeFair tag. So I'm going to place a MeFair ultralight C and click on the connect. I'm not going to use this thing, so I'm going to take it away. Now it looks bit weird here because I know what the problem in the software, and we still haven't fixed it. Now once you establish the connection, you can place this SRI512 tag and choose this. So in this tab you're going to see all the commands that are used in ACR122u, and this is going to show you the user data. You can modify user data. The OTP, we have got 5 OTP blocks, and the counters and the system area. So first thing you're going to activate. Now these are the various commands Okay, so first probably now I will show you how to use, then I will go back to this commands. The first thing you do is hit the go. Now this is going to bring all the 16 blocks plus the system area into this software, and what you see here is the default values. The default value of of this OTP are all FFs, mean that is not used, and in fact the default values of this area is also FF, but I might have changed that to 00. Now I'm going to clear that. Let's try to do a simple read and write operation for the user memory. So I'm going to go to user area. I'm going to click on select, say ABCD. You can type and write. So the write is successful. If you look at here, now there's something, all these commands are specific to SRI512. Now write is successful. Probably I can use this section to do some bulk writing. Now let's write number 1000. This is the hex equivalent of 1000, and write from 8. So you can see that the writing is done using here. The B0 stands for the lower byte, and this is B3 is the higher byte. I've got a column for locked, and the description tells what type of block is this. If you go to the counter or the system, so there is a command to get the UID. Now get UID. Now this is the 8 bytes of UID you get, and this is decoded here. The first byte D0 is always IS1443B tags, followed by the manufacturer code. 2 means ST microelectronics, followed by 06. Now there is a document on internet that explains how to decode this information. Now 06 means SRI512. I think 04 probably it is SRIX4, I suppose. Yeah, anything left out is taken as a serial number, and none of the blocks are locked. And in this section I'm decoding each bit, showing that the 16 bits that are stored in the system area corresponds to 16 blocks from B0 to B5. Now you can go and lock again. Probably locking I will try on a different tag, because once you lock it's all gone. So let's try the counter. So the counter, what you see here is the default value of the counter. Now the counter here, you got counter in block 5 is here, and counter block 6 has got some special feature which I have shown here as a reload counter and a normal counter. So let's use this the counter in block 5. This is just a normal counter, and this is always a decrementing counter. I want to reduce this to say 00. So as soon as you type, you see the hexadecimal equivalent here. When I click write, now the write is successful. So likewise, you can use this as if you forget about this concept of reload counter, you can just use this as a 32-bit counter. So I'm going to change the normal counter. Basically the documentation also says from the 32-bit value, the higher 11 bits are called as reload counter, and the remaining 21 bits are a normal counter. So I'm going to reduce this to, so keep in mind you cannot increase the counter value, you can only decrease it. Now there is a logic built into the chip itself that will prevent from increasing, and the software also doesn't allow to do that. I have got error message here. Now we are able to decrease the counter. Now that's how the counter works. Let's play the OTP. Now OTP, now there are so many functions of OTP. It's called write-ons, and one of the best application is the ticketing. So each bit can be considered as a entry, as an entry into a museum. You can have so because there are 5 OTPs here, you can create a ticket with the entry to 5 different museums, where the OTP, the block 0 can corresponds to one museum, the block 1 corresponds second museum, and so on. So I'm going to put a tick here, and I'm going to say write. As you see here, as soon as I put a tick, the actual hexa value is shown here as well. So I'm going to put 2 ticks and say write. Now the OTP is written, and again, if you look at the commands here, everything is just a ordinary write block and read block. Now if you try to, I'm going to write some more bits, and I'm going to remove the one that's already written. If you say write, now we got a write error because we try to reset the value already set in the memory, which is not possible. And if you read this documentation, it clearly says there's a section somewhere down how the OTP works. Now you cannot do that. Now I can just put some more ticks, but I can't remove any tick there, right? Now write is possible. Likewise, you can also assume that I want to set all. Click this S, it sets all, and write. So I have set. Now the documentation says when the block value is all zeros, it says this block has an empty block, and you cannot write any further. You can remember this word empty block. So likewise, I can that's how I can play with this OTP, and keep in mind OTPs are one-time programmable. I'm not worried too much now because I can always reset. That's the reason why it's called resettable OTP. I'll show you how to do that. So I'm going to close, take the card out, put it back again. This time you don't have to go through that lengthy process of having any MeFair attack. Just click this, activate. Sometimes if the reading throws an error, just try to place this move up and down and find the right place. Probably depends on where the antenna is on the box. Now you can see all the things we have done so far. If you look at the OTP is showing what we have done, and here the OTP2 is all set. Now that's all. If you look at this the structure, this card is a very easy to use stack. Now next thing is about how to use this reload counter. Now what the documentation says, when I click on the write command, so before the write actually takes place, we can introduce what is called erase cycle. So erase means the memory you can erase the existing memory, so which is automatically done by just writing a number which is smaller than the current number. Now I don't want to use Control Z. So the default, the initial value is 2047. It means you can reload this 2047 times. So I'm going to first write 2056, right? Now automatically the software says the auto erase cycle is enabled. Now all these OTP bits that are ticked, I'm going to clear. Click on this C and write. Look at that, the write is successful. We just reverted back the OTP bits. I'm going to clear everything, clear that. Okay, so now my OTP is back to the way it was when we had this the new tag. I'm going to close this again, place it back, activate. Okay, and that's all. Okay, we can, okay, sorry, I mentioned about the locking. I'll show you how to lock this using a different tag. I'm going to close this. This is the tag I was playing with. Activate. So I have already, yeah, there are so many interesting things to discuss here as well. So this tag is a bit different from SRI4K. We can lock all these 16 blocks, including you can lock here. You can see this is an example where I have locked the OTP. I have locked the counter. I've locked OTP here. I've locked the counter also. Then I've locked in a user memory. So I'm going to write and see what happens. And keep in mind, you cannot undo the locking. So you just have to keep in mind it's not at all possible to unlock. So I'm going to go to block 7 and write 10,000. Right. Now read after write did not match. Okay. Now we know from the document that a write operation does not return any response. So the only way to make sure the write was done is to compare what we tried to write and compare with the data we got after reading. Now since these two didn't match, so that's error. So that proves you cannot write to a locked block. How about the counter? So I have a counter here, counter number 5, which is also locked, but I'm going to counterfile this one. I'm going to reduce it, try to reduce. We're trying counter 5. Okay. Right, the write failed again, the same concept. You try to write something, but the read did not match, so it is an error. So you can lock a counter. Now the question is, when would you like to lock a counter? I think these are the features of the tag, and you have to design your system using these features. There could be some applications where the counter can be used as a data and you can lock it. And OTP, again same thing. Why would you lock the OTP? Again, these OTPs can be used as a normal data block or normal user block, and you can, once the data is written, you can lock it. So we are going to see the OTP here, which is locked, OTP 1. I'm going to try to set something, right? Write error failed because locked. Try to write it to OTP 1, right? The write is successful because this OTP is not locked. How about introducing a erase cycle and writing the OTP 0? Go to the counter. The reload or the erase cycle is introduced by writing 1 less or any number less than the existing one. Right. Now if I go to OTP, so go and try to write to a locked block. It still shows an error, and go and write to clear the second OTP in block 1. Right. Now this is successful. Okay. Now I've tried something here which I don't want you to try unless you know what you're doing. I somehow changed the chip ID in this tag to 0. Now after that, I'm going to show you what exactly has happened here. Now we have seen in the last video, whenever we send initiate command to SRI512, it generates a random chip ID and returns that. Whereas now I have written something for the chip ID. If you see the documentation, it says if you write anything here, it will start using this chip ID. I'm still not very comfortable with what exactly it happened. Probably once I get the information, probably I'll let you know as well. If you activate with the initiate command, I'm getting this fixed value 0. Okay, so looks like after writing any value here in the chip ID, I think that's the value that will be used for all the initiate command. Okay, I think that covers everything we need to know about SRI512. Let's quickly go through some of these commands, and you just have to relate the commands with the commands you see in the document. So what activate does here is it's trying to use the PN532 command called inList passive target command. It's a D4 A0, and these two bytes tells PN532 to use a type B. However, the outcome of this request is 0, that is no tags are found. This is a kind of a workaround, I suppose. Now, because the way this tag works, so we don't have to activate this tag, because as soon as you bring the tag near the reader, it's always in the ready state. Now we are sending the initiate command. You have to see the documentation for this command structure. Now with the initiate command, this is the response we get, the 0 0. I think not, sorry, I think it's probably the B7. I think, sorry, it's B7. I was wrong, I said something about zeros, I apologize for that. So here, even though I've got a fixed ID, chip ID set to 0, okay, I think we still get a random number. So this is the chip ID generated by this tag. You get B7, and the next is the select chip ID. This is the select command. The outcome is the chip ID is returned back. Then I'm using the get UID. The reason I'm using this command is to know whether this is SRI4K or 512, because the same screen is used for both SRI4K and 512. So depending on the type of the tag, which you can find out from this response, so we can find, we can decide, or we can configure the screen. Now after that, when you hit the go, I'm sending a series of read block. So read block 0, again this command matches what the document says, and this is going to return 4 bytes here, 4 bytes, and these are the 4 bytes correspond to the data here. So this will go up to block 16. Here, I think the block 16 is error. Probably that's how the software decides when to stop. Probably you can ignore this command. And I'm reading block, the last system area block, which is block 255, and you got this output. And after that, everything, it's either read or write. It just manipulating these bits. If you work here, combine this into a 32-bit and write it. Everything is a read and write. Even though you see all the checkboxes here, eventually they are converted to a 32-bit. And if you try to write, so here also we are sending the write block command to block number 8, and this is the 4 bytes, the write data. Again, if you look at the way the data is sent, the lower byte is sent first, which corresponds to B0. Then obviously, if you look into this PN532 documentation, this is a timeout error message, and we know that you don't get a response from write. Now I'm reading it. I'm reading the block 8 again here. reading block 8, and I'm getting back the 4 bytes, which now the software compares and says it's a successful write. I think that's all about SRI512. In the next videos I'll be showing a very similar screen but using a different types of readers. Thank you.